So up to now, we've been talking about forces. We talked about work and energy, and we've talked about kinematics. Those are three key pieces for analyzing things. They handle a bunch of different situations. There's a next one, and I've got to hit pause on this video, just a sec. The next one is momentum. And so let me just put up some terms here. And if you want to follow along, if you don't want to write down as much, you could look on page 31 in your book. Maybe I'll just show you a quick screen share and I'll scroll through that just in case that's helping you with the video. So the symbol is P. It's a vector. So you have momentum to the right or to the left or up or down. Okay, collision time. It's strictly speaking a delta t, but sometimes I get lazy and shorten it to a t. The collision time is the time that two objects are in contact with each other. And then there's the average force. It turns out this is a way you can get average force, the change in momentum of an object divided by the change in time. And the change in momentum is a term that is called impulse. Okay. Now, where does this come from? Momentum. Well, I wanted to say one thing else. Let me start here. Before I talk about where it comes from, I want to mention that up till now, I don't know if you noticed, but pretty much most of the time we're talking about a single object translating. It's moving around, and sometimes it was a group of objects translating in unison. We haven't talked about things hitting each other or bouncing off each other, right? So this is the tool that handles collisions, momentum. So that is why we need this new tool. It's a convenient way of doing it. Where does it come from? I think I have this on the next page. So at the top of page 32, I did the derivation for you. This little puppy right here is Newton's third law. Let me get my annotation. This is Newton's third law. The force that 2 exerts on 1 is equal and opposite to the force that 1 exerts on 2. If we use this new definition of force, it turns out, for example, you used to say force is equal to ma. Well, it turns out the more correct statement, what if mass is changing? It turns out you can actually handle this by saying it's actually equal to d dt, the time derivative of this new quantity momentum. Believe it or not, this newer definition is valid in relativity as well. So even when things are moving near the speed of light, the upper definition is not valid at speeds near the speed of light. So that said, for most problems we do, if mass is not changing, right? Okay, that's fine. But that's basically why we're going into this new upgraded equation. Enough on that. So, okay, Newton's third law. Here's our new definition of force. It's change in momentum over change in time. Well, the change in time is the same. So this says the change in momentum of one object is equal and opposite to the change in momentum of another object. If we add that to the other side, we see that the net system momentum doesn't change. Wait, that's a conservation law. We're saying P initial equals P final. Momentum is conserved. Just like energy is conserved, we are going to assume momentum is conserved. Be careful. It's sort of like energy is conserved all the time in the universe, but it's very complicated and sometimes there's a work term. Just like that, conservation momentum is not so easy to implement, right? We know that in general, the initial momentum should equal the final momentum. However, it can be complicated seen in certain cases. So here are some practical considerations for solving momentum problems. Okay. First, is it appropriate? These are the situations right here. If these things are true, usually you could do a momentum problem. Is it a collision or an explosion or a change of shape with negligible external forces? Do me a favor and underline that. It's not obvious when external forces are negligible. That's what I'll show you when we start doing problems. When can you ignore external forces? Now, if the collision time is small, even large external forces can sometimes be considered negligible. Okay. And then what are we going to do? Draw pictures, list equations, look for some keywords to see if we could use this extra trick, reread, plug in zeros, solve for something. All right. So that's our momentum strategy. And I'll just go back up to here. Here's our momentum definitions. Why I didn't put them all on the same page, I don't know, but whatever. All right. Any questions about that? These definitions or any of these terms? We're going to do problems to learn what they mean in a minute. By the way, I keep telling you that coding is coming. That's why we're doing this, and that's why we're getting into this lab this week. So I promise we will finally start doing coding. This is a big deal. It looks like a footnote, but this is called the Euler-Kromer method, or ECM. Okay. This is a technique where you can write a computer code and the outputs of your computer code obey conservation of energy. So it's basically a way to code physics that conserves energy, which is a big deal. We expect energy should be conserved. So what are we going to do in this thing? The first thing you do is first calculate force, and then you rearrange this equation right here. All of this crap, all these equations, basically, you rearrange them and say, oh, there's a way to figure out the new momentum. You apply a force for a small amount of time that gives you the change in momentum. We can then compute the average velocity, and then we could do this trick that I alluded to in the first lecture. We're right there. You could say, okay, now I take that average velocity times time and use that to update the position. You may say, well, wait, what if it's accelerating? We accounted for that in the force doing the momentum update. And then that information is carried into here. So we've already accounted for the acceleration when we do this. And that's why it's okay to use distance equals rate times time. And what you do is, if you're getting a bad approximation, you make delta t smaller. This is a big deal. Okay. Euler-Kromer method. Any questions about that? All right. All right. Let's get to a problem. Let's start with this one. We got to start simple. Okay. We've got a bouncy ball. You're going to throw it at the wall and do some stuff. So I'm going to get my board erased and we're going to work through this on the whiteboard. Okay. I don't know if you could tell, but I'm getting pretty excited. All right. We're getting into some interesting stuff now. Things are going to start moving, colliding. Super fun. Okay, so there's a before picture and an after picture. That's a hallmark of any momentum problem. You better do both. Okay, so here, okay, so before it's going this way, and I think it said it's going that way. It's 6.0. And then afterwards, it's going the other way at 4.0. And then we have some parameters here. We're told the mass is 0.075 kilograms. So it looks like we're doing 2 sig figs for this whole problem. That's fine. Okay. I'm reading this line right here. This is an important line. During the collision, obviously the wall, it hits the wall. Gravity is not 0, right? However, look at this tiny collision time. The amount of time that gravity is acting on there would cause a negligible change in the velocity. So we're going, so we're going to ignore that. And so we're only getting an approximate answer. This is not perfect because we're ignoring that force due to gravity during the collision. Again, because the collision time is very short, I think it's reasonable. This is going to be a good approximation. Is it perfect? No. All right. So we are asked, all right, so now I think I've got it. Let me get this book over here. Move this thing a little bit. All right. First question is, what's the initial momentum? Okay, let's not overthink it. What was momentum? Does anybody remember the equation?
Mass times velocity.
Okay. So what do you get? Punch it in. Let's do it. Give me a number. Give me the answer to that. Let me find a calculator. Where did I put that? Oh, it's right over there, I think. Shoot. Calculator. Come on. Here's one. Okay. What do you get for the momentum?
For before or after?
For before. Aren't we doing the initial one is before? Initial momentum
0.45.
Okay. And then what would I immediately say to you at this point?
Units.
Okay, good. What else? What are the units then?
Be kilograms times meters per second.
And that's just what it is. It doesn't have a special unit. So we're okay. All right. And then what else would I say? Look at that definition carefully. I made a mistake here. This is wrong.
The arrow over there.
The arrows, right? So the answer should be
Negative.
negative. And I'm going to put the negative I hat right here. Does that make sense?
Mhm.
Strictly speaking, momentum is a vector. We have to be a little bit picky now. So you got the idea. So you could either say it's, now here's the deal. A lot of times what people would say is we'd say P initial X equals negative 0.45 kilogram meter per second. And so then, this implies the I hat for you. And we don't write the I hat and we still have the minus sign. Let me pop that, make that pop. So once again, we see I spend a lot of time talking about minus signs because those are the details that cause you to miss points when you actually understand the physics. Every minus sign is like a secret, precious nugget that you must cherish and whatever. Okay, so that's part A. Is everybody cool with part A? And I'm just going to write it up here. Negative 0.45 kilogram meter per seconds. Done. Okay. So part B, just punch in the number so I don't have to do it all. So we'll call that P initial, P final, and I'll say that's P initial X, and we'll call this initial X. Get rid of that vector now because I wrote the X, right? So we'll say P final X is equal to M V final X. What's that going to equal in this case? Just take that previous answer, divide by 6 times by 4, right? So 0.3. Is it positive or negative in this case?
Positive.
Yeah, so positive 0.30. Okay. So, all right. Part C says, what's the change? What's the change in momentum in the X direction?
.75.
Yes, it's not 15. Got it? So, and is it positive or negative?
Positive.
Positive, because I went from a negative to a positive, I must have changed in a positive way. Something I generally try to avoid since I'm such a negative person. Ha, ha, ha. All right. So the change in momentum is 70. Yeah, it's not 15. So that's what I wanted to stress in this. I hope this makes sense. When you deal with momentum, you got to remember not only the units, you got to remember the plus minus sign, and then changes in momentum. You got to remember when you're subtracting to include that minus sign. So final minus a negative initial becomes this huge thing. All right, got it. All right. So now in this case, let's see. What was the next question? Oh, what's another name for this change in momentum? What's this called? Impulse. Okay, so that's the symbol J. Impulse. Great. Just a term. You know what it means now. Okay. And if I want to get the average force on the ball during the collision, here's how you do it. The force average on ball, and I'll scoot the board back in just a sec. It's a vector. Force is a vector. It's equal to the change in momentum of the ball divided by the change in time over which that occurs. Sorry, that's so glary. So in this case, the green is kind of hard to read. Apologies there. But the force average on the ball, basically you take delta P over delta T. Got it. So in this case, I'm going to punch that in on my calculator. You could punch it in on yours. It's this number divided by that number. I don't want to screw this up. So 0.75 divided by 0.05. That's 15. Oh, that's cool. I got 15. Again, the first digit's a 1. We oftentimes keep an extra sig fig compared to the rest of the numbers if the first digit is a 1. This is reasonable. Wait, this is wrong. What did I forget?
Direction.
Yeah. Which direction is it? Well, this was
Positive.
Positive. I had. Think, does this seem reasonable? The ball was going this way. Now it's going that way. Which way did the wall push on it? That way. Positive. Got it. How could we figure out the force that the ball exerts on the wall?
It's just negative of that.
Exactly. Newton's third law. Ball on wall, 15 that way. Wall on ball. Hey, who needs Dr. Seuss when you've got me? I don't know what's going on today. I'm losing it, people.
So I don't understand the force average.
Yeah.
So I'm thinking like as soon as it hits the wall, that's the force at that instant. But you're saying the force average is during this time period, right?
Yeah. Do you remember when I let me go to some videos? Can I do some videos really quick?
That's fine.
All right. So I have some ready, I think. Now, let me go to here. I was going to do this one next. This is a ball hitting a wall, and we'll talk about it. But let me see if I can get another one here. Let me see if I can do YouTube. Let me see if I can figure this out. All this junk. Let's see. This one. And then this one. And then I think we talked about this in chapter 5. Remember I dropped a ball on a scale in chapter 5? So give me a sec. There it is. Okay, so this is a force versus time plot. So just to be clear, this is time on this axis and this is force up here. Okay, that's what that's going to be. Now I need to clear that because the thing's going to move around. But I'm going to drop a ball on here. Okay. All right. So now the idea here is if, again, this is time in seconds. Hopefully you could see this. And this is force in newtons. And so during the collision, this right here looks like that's about a change in time. So I'll call that dt, or a small time increment, or delta t, however you want to say it. Is that about 0.2 seconds, I think? Maybe? I don't know. Something like that. Okay. So again, each one of these tick marks is 0.1, 0.2, 0.3, 0.4. So I've just seen it's basically 2 tick marks there. So that's where I got the time. Now, the idea here is this isn't exactly the same as what we did, but the average force would be something like this value. About, for this case, it was about 150 newtons or so. So maybe it was 175 newtons on average. So Esteban, that's what I mean by an average force for this problem. Are you okay with that?
Yeah, it makes sense now. But I was thinking that for some reason in my mind, I was picturing the crash to be like instantaneous, but obviously the duration of time we're talking about is the time it's of impact.
Yeah,
So
because the ball, when it hits, it's going to squish and flatten out,
Mhm.
and then it's going to spring back and launch upwards, right? And
Yeah.
so you can think of any real object for that piece of time as being a little bit like a spring where it squishes and bounces back. Now, some springs are shittier than others, and some springs, like this medicine ball, are terrible. And so they lose a lot of energy when they squish. So there's a lot of dampening inside the medicine ball as it squishes. So you lose a ton of energy, and that's why it doesn't bounce up as fast. Now, if we go back to our worked problem here, hold on, I can do this. All right. In this one, we see we lost a little bit of speed, but not nearly so much. So this collision is more elastic, as we say. More on that in a minute. Basically, if you have a collision where you lose no energy, we call it elastic. If you have a collision where you lose a little bit of energy, we call that inelastic. And then if it loses so much energy and they stick together afterwards, we call that perfectly inelastic. Again, I will review that all later. You don't need to write those terms down now. I have that all written for you in a minute. So this is very similar to this problem. Is that good on that one, Esteban?
Yeah.
All right. Now let's check this one out. If I can find it. Maybe. No, wrong one. Wrong one. This one. Let's go to this one. Okay, so I'll talk about this while it plays, and let me just mute this here. So the idea here is I have some balls, and you can look at the scale readings. They're both about the same mass. They're both about 40 grams. Just let me show you this here. 36.8, 36.3. So those two balls have the same mass. Okay, and now watch what I do here. Wait, let's play that back. Let's get a running start. I'm going to pick the balls up and drop them. Give me just a sec. Sorry about that. So look at this ball. It doesn't bounce very much. Okay. Now look at this one. It's much more bouncy. So I'm going to drop it from the same height. And what I'm going to try to prove to you here is when you drop the bouncy ball from the large height, which one is going to cause more force? The bouncy ball or the ball that doesn't bounce much? What do you think? So again, we have a bouncy ball and a not bouncy ball. Which one is going to cause more force on the board? Or is it the same? Not bouncy? Almost knocks it over. What's the bouncy one going to do? Knock it over, not knock it over, same amount. What do you think?
So my intuition tells me that they're equals to the same mass, and so they're going to have the same velocity because they're on the same placement of the
Right.
curve. But for some reason, I want to say that the bouncy ball is going to exert more force, which doesn't make sense to the equation.
It
But for some
doesn't.
reason, because
Let's
it's
review. Remember, what's the momentum equation, right?
Mass.
Force is related to, well, let me, hold on. What was that force equation? How did force relate to momentum? Do you remember?
mass times velocity.
Yeah, but how does force, what was it equal to in terms of momentum?
Oh, the change in momentum
Change. That's what I'm looking for. Which objects tend to change momentum more? Objects that are
okay.
So think about it. The bouncy is coming in this way,
It's gonna have
and
more
then it
change in
goes
momentum.
back. So it's got almost twice as much change. Think about that. Versus the non-bouncy. The non-bouncy is coming in same speed, but what's its momentum afterwards if it's not that bouncy? 0, right? Changing from plus to negative is twice as much as changing from positive to 0. You get twice as much force with a bouncy ball as a dead ball. Does that make sense with what you were asking about?
Yeah, that's very interesting.
So let's see. I'm going to drop it. So let's run this video back one more time without all this crap written on here. And let's just watch it. So keep an eye on where I place the balls. I tried to put them at the same position, but let's just start from the beginning and get a running start. It's only 30 seconds. Same masses, essentially, within a few tenths of a gram. The white stripe was just there so I could tell the difference in the video. This is the dead ball. It's put on there right about there, right near the black, right above the piece of wood. Much bouncier, same spot. And we're able to get more force with the bouncy ball and actually knock this thing over. So I'm not lying to you here that we have to treat momentum as a vector. That's what that was for. Cool? Whew. It's a tricky one. It's a lot easier to show these demos live.
It seems like I was getting confused. Momentum versus the force that comes from momentum.
Yeah. So remember, momentum is linked to, changes in momentum. Changes is relates to force. Got it?
Yeah.
So it's not, it's dp dt. And that's what gets us. And that's the other thing is, right, when the ball bounces backwards, the magnitude of momentum doesn't change much at all. But that's because you change from a positive direction to a negative. So the change in momentum is actually huge when you reverse direction. This is going to be a theme that pops up all the time. Think about this, right? Maybe you're thinking about, how does a balloon stay inflated? Tell me. You blow up a balloon, why doesn't it collapse on itself?
Well, the pressure inside the balloon is equal to the pressure outside. Is that what you're referring to?
That's not true.
The atoms inside the balloon are pushing outwards.
Right, and they hit the wall and then they bounce off. The force that pushes outwards on the balloon is from moles and moles of air banging into the wall and doing exactly this problem. And that's what keeps the balloon from collapsing on itself. And there's so many atoms that on average at any one time, there's always a bunch that are pushing outwards. Now, keep in mind, when you blow up a balloon, the membrane is under tension. So it's actually slightly higher pressure inside, right? It's a slightly compressed air inside there. So it's not exactly the same pressure as outside.
No, I know. I got confused there.
All right. I know what you were going with, though. Yeah. And pressure and force and that relationship we handle in chapter 14. And since we discussed chapter 14 now, let's just call class done for the semester. I quit. Oh, wouldn't that be nice?
And we all get A's.
Oh, shoot. I'd have to do that too? All right. Well, maybe we'll keep studying then. All right. let's get back into here and see if we could learn a little bit more before class ends. Whoops. Oh, I don't want that playing in the background. Hold on. I think I accidentally hit play. Come on. Oh, whoops. Wrong one. This one. Oh, there's a collision. There's different types of collisions here. So look at these terms that I'm going to use in this playlist. Perfectly inelastic, elastic, inelastic. Notice there's a difference between inelastic. And so if you look at, let's just run a collision and see what these look like. The idea is I have two different carts there. And notice after this collision, we see that these we see that these two photo gates are recording the initial velocity just before impact. So these two things here record the velocity. And so I'm trying to show you that even though I was doing these by hand, they are going about the same velocity when you hit. Notice these are each 300 grams over here. This one is 200. The one in back is 400. So when a 300 gram slams into a 400 gram mass versus a 300 into a 200 gram mass, we could make our prediction which one should be moving faster, right? Hopefully you agree the blue one is moving a little bit faster there afterwards. Whoops. Let me get out of here. There's these, and I'll go through a spreadsheet on, here's an elastic explosion. Whoops, let me get my annotations off of here. So what we're going to try and do is apply the same math to these scenarios, and we'll do example problems next time. But so here's an example. I don't know if you can see this. There's a 200 gram and a 400 gram. Let me make it a little bigger. And the idea is there's a rubber band right here. So there's a rubber band, and what I'm going to do is I'm going to squish these two together and let go of them. And they're going to fly outwards. The rubber band is acting like a spring, and it will conserve energy. And so when we do this, these two photo gates this time are recording the velocities after the explosion. So if you had to guess, when we run this experiment, I'm going to squish them together. Which one should be moving faster after I let go of it? The 420 or the 210?
210?
The 210. Which one is going to exert more force during the separation, during the explosion, so to speak?
Equal force.
Which one has more, which one has a longer collision time? Somebody other than Esteban, I guess. You could do it. Be brave. Take a chance. It's okay to be wrong.
It's the same.
It's the same. Good. Thank you. All right. So we have the same collision time. We have the same amount of force, but the accelerations differ. And so that's why we get different velocities here. Newton's third law, momentum problems, they go hand in hand. So when we look at this one, hopefully we see on the screen, the blue one should be about twice as big as the red one. I don't know if that made sense there, but let's get my annotations off. We'll run this experiment sometime. I think if I just let it play, that's the fastest way to do this one. So I'm going to squish these. It's not perfect, but pretty close. All right. So that's a version of this elastic explosion. Whoops, we already saw that one. So let me get back to here and let me see. All right. So right now I'm starting to just show you, this is kind of the stuff we're going to try and analyze, things colliding. And if you want, do I have me pushing a chemist around? Right. Let me do a couple more really quick and just get these over with. So let's do this. So I'll gloss over this. That's the medicine ball. That's Angus. He's the guy that helps me make all these videos and posts them and helps me organize. So he's the man. So what I'm going to do here, he weighs about 145 pounds. That's a little hovercraft that we normally get students on. There's some meter sticks there. The piece of blue tape is 2 meters. Oh, and so when he throws that ball, think about this. That ball weighs about 6-7 pounds. He weighs about 140. So when you throw a ball to the right, he actually moves backwards to the left. Now, in the real world, you're not sitting on a hovercraft all the time. And so as a result, you don't feel yourself moving backwards as much. and your feet are experiencing a frictional force that keeps you from moving backwards. But when you throw an object to the right, you recoil to the left. That's one thing that applies here. Let's look at another one. So there's me, and I think we got a special guest. For some reason, Gottlieb was around. Oh, did he show up? Oh, this is me and Angus. I see. And so we're just going to push as hard as we can. And the idea is I weigh about 240. Angus weighs about 140. And we see that the same thing is now happening to Angus. And oh, there's me. I was laughing yeah. So, and then I started laughing so hard I had ab cramps. So that tells you how out of shape I am. But here we see, again, I was trying to show the difference. Angus pushing on the ball, right? The ball is the low mass object. It experiences the large acceleration. But what if Angus pushes against a huge beast like me? Then he's the object that experiences the large acceleration. So it's the relative masses. Okay. If a mosquito hits a school bus, right? The mosquito has a huge acceleration. The school bus experiences almost none. And then just so we can taunt the chemists, let's get a chemist in here. Maybe. This one worked a little better, I think. So again, the masses are the same. That's a scrawny little chemist, Gottlieb, and he's 145 pounds, whereas I'm about 240. So when we do this, we actually got it. Angus is better on the camera. So those are just leaf blowers. And so you could see that I'm moving slower than he is, and the ratio is about right. All right, so let's stop there because I don't know if this is helping or not. But what am I trying to show you here? Momentum is going to apply whenever two objects hit or push off each other. That's one thing. There's this term impulse that we talked about, right? Impulse is the change in momentum. Change in momentum is what relates to the force. And then if I could go to the screen share, let's get the notes and then call it the day after I see this one last thing. Whoops, let's get this up here. Okay, 9.2 is a good question to do after class. That'll kind of revisit this. There's our problem solving strategies on page 31 and 32. And then we'll pick up here next time. These are, you could see some problems that we're going to talk about, but these are the types of collisions. So this is the last piece of theory. So if you're curious about these different names that I've been using on page 34, so we see page 31, 32, and 34 have all the kind of notes. The names I use don't necessarily match up perfectly with textbook, but usually they do. Most books usually just give these three. All right, so for me, there's a perfectly inelastic collision. That's one where the two objects collide and form a single mass. Energy is lost. So we say the objects stick together, the momentum initial equals the momentum final, but not the energy. An example problem would be 9.6. If they are elastic, we say it's perfectly bouncy. This is the special case. Energy is also conserved. The objects do not form a single mass. The initial momentum equals the final and energy. Two pool balls colliding is actually very elastic. Steel balls hitting each other, or if there's a spring between two objects, that's elastic. Most real-life collisions are called inelastic. They are imperfectly bouncy. Momentum is not conserved. Energy is not conserved. They don't form a single mass. So most of the time, like when your car hits another car, hopefully it doesn't embed in the other car and form a single mass. If it does embed and stick together, that would be two cars getting stuck together. That would be perfectly inelastic. If they bounce off each other and fly away, that's just called inelastic. So that's the difference between perfectly inelastic and inelastic. And if you have an explosion is like a perfectly inelastic collision played in reverse. Energy is gained, right? You take some chemicals like, I don't know, TNT or gunpowder or C4, and that releases chemical energy and turns projectiles out of it. You create kinetic energy out of chemical potential energy. So, right, that's usually where that comes from. So initially the bomb might have some speed, and afterwards fragments have speeds. So there's a couple of cases there. Now there's the last special one that I use, the elastic explosion. That's an explosion. Notice here, energy was gained. You can have an explosion if there was a spring used to push apart the two blocks, or magnets, or something like that, or a block slide. So these types of problems show you a case where you could have an object where two blocks spread apart, energy is also conserved, and those are the examples. Woof. That's page 31, 32, and 34. It's a heavy dose of words. Sorry for that. We are going to pick up on this next time. Before we end, I see we have 7 minutes. I'm going to give you a quick concept question to see if any of this makes sense. All right. Before I do that concept question, does anybody have any questions for me about any of this? All right. And like I said, you don't really learn it till you get in there and start doing problems, right? So, all right, let's do a quick problem here and end the day. All right, so let's go back and catch up one of these that I missed. Let's look at this one. Take a second, think to yourself. You don't have to answer to me. I'll give you 1 minute on the clock here. So at 2:10, I'll go over the solution. School bus drives to the right, hits the insect. Bug sticks to the sticks to the windshield. All right, let's go for it. What do you think? Anybody now? Part A. During the collision, which one's exerting more force, the bus or the bug?
Neither. They're both exerting the same amount of force.
Same amount of force. Who has the larger change in momentum? Somebody else.
Mosquito.
Equal change of momentum.
Same. They have the same change in momentum. Now, change in velocity is different. Okay, but change in momentum is the same thing as force. Remember that? Because force equals delta P over delta T. So watch out for that one. That's the sneaky one, right? Okay. Which one has the larger acceleration?
The bug.
The bug. If it helps, think about the change in momentum of the bus. That should be equal in magnitude, but opposite to change in momentum of the bug. Now, you might be saying, wait a minute, what's up? Well, remember, the bus has a huge mass. As a result, it has a tiny delta V. On the flip side, the bug has a tiny mass, so it has a huge delta V. And then I need a minus sign. So it's not that the bug isn't affected more, but when you look at momentum, momentum is defined as mass times velocity. So changes in velocity versus changes in momentum are very different statements. And that's probably what you were thinking of. I don't know. Did that address that one, whoever that was? Is that good? Yeah. All right, cool. Let me see this. What type of collision is this? When the bug hits the bus and sticks to it. Do you remember?
Inelastic.
Perfectly inelastic. So yes, it's inelastic, and we usually add the adjective perfectly to that, just because when they stick together and move in unison afterwards, yeah. Okay. So in this case, how about let's look up here. This is kind of a fun one. Suppose one day, I see we have 3 minutes, so we might as well do this one. Suppose one day everybody on Earth decides to gather at the North Pole and jump. How much is this going to affect the Earth? What would your gut say? How many people are on Earth? Give me a number.
There's like 8 or 9 billion or something like that.
Can we round that to 10 billion?
Okay.
So won't that be 10 to the 10th people, approximately? Okay. So let's just say that. What's the mass of one human being? On average, just take a guess.
60 kilos at least.
That sounds good. And now that's going to be hard because that's got a 6 in it. So I'm going to round up to my mass, 100 kilos. Okay. So let's just say everybody's 100 kilos. What's the net mass? Well, this is 10 to the 1, 2. Isn't it 10 to the 12 kilograms? That's about the mass of all the people on Earth. And that's an overestimate. We overcounted the number of people and we said everybody's as big as me. Clearly false. Now think about this. How big is the mass of the Earth? Look at how much bigger that is. Now let's get this right. 10 to the 6th is a million. 10 to the 12th, or whoops, 10 to the 9th would be a billion. So 10 to the 12th is a trillion. The mass of the Earth is a trillion times bigger. Even if people are jumping here at 5 meters per second, which is insane, right? Well, that's maybe doable. I'd have to sit there and think about it. You could go through the calculation here, right? We know that V is equal to the square root of 2GH. So that's 19.6. What's the largest you jump? Maybe a meter high? That would be insane, right? That's like a professional athlete. So 19.6 times 1. So square root of 20, basically, right? So square root of 20. I'm just punching in the numbers. Square root of 20 is about 5. So this would be elite athletic jumping ability. Vince Carter, Michael Jordan, something like that. I don't know. So yeah, imagine if everybody was as big as me and could jump as high as the best basketball player on Earth ever, right? You would be looking at, the Earth would move downwards when you jump about 5 meters per second times 10 to the minus 12. Somewhere in there. Now, I didn't do the math exactly, but it's a trillion times smaller. So it's not that the Earth doesn't move the other way, but even if every single human on Earth was huge and super athletic and jumped all at the same time, the Earth would still move less than a nucleus per second or so. This is ridiculous. It's so small, right? So, or maybe a size of an atom, right? So we might be able to make the Earth move about an atom's width. And then what's going to happen is right afterwards, it's going to come right back. So I don't know. I hope that's slightly interesting to you. We don't really have to worry about that. Accidentally pushing the Earth away if we all jump at the same time. Whew. Sleep easy tonight.